Welcome back to another lecture from Organic Chemistry. In this lecture, I'm going to go through infrared or IR spectroscopy. And we use IR in organic chemistry a lot to characterize actually functional groups. The main application of IR technique is going to be going after functional groups in organic chemistry. Okay, we're going to use wave, or we're going to use light to technically identify what type of bonds we are dealing with. So because we are dealing with waves, we need to know some stuff about waves. The first thing is going to be frequency, wavelength, and amplitude. Okay, what's a wavelength? Wavelength, you have a wave in front of you, and that wave, it has two parts here. It has phase, forgive me, phase. It can be positive or negative. Okay, and next thing is, as you see here, when we have a wave that's going up and down, and this one keep going on. And other x's, we have time here. The distance between two identical points, if you measure two identical points, let's say these two, the distance between them, we call it wavelength. So this is going to be the wavelength, and the wavelength, we show it by lambda. The unit for it will be in meter. So lambda represent wavelength. And next, the distance from the horizontal, from max point or minimum point, max or minimum point to the horizontal line. Okay, so I'm talking about technically these two. Okay. This one, we call it amplitude. Okay. Amplitude, we'll be talking about the intensity of the light that you're using. Okay, next, number of cycles that they pass one specific point in 1 second represent frequency. So frequency will be number of cycles per second. Okay, number of cycles per second. Okay, let's count the cycles. I want you to be careful about the slope of each wave. Okay, slope here is positive. Okay, and when it hits the maximum point, and slope, it will be negative, and this one keeps going down negative until here, until we hit the minimum point. But when we hit the minimum point, now the slope, it will be positive. So please don't say the identical point of this, for example, this point, the identical point for it is going to be there. Okay, and that should be the wavelength. No, because this one, it has a positive slope, well, sorry, negative slope on the left side and positive slope on the right side. So these 2 points are not really identical. Okay, that's one. Next, and we said frequency is number of cycles per second. Frequency, we show it by nu. Okay, this is the this is the symbol that we use for it. And frequency, it has a unit of 1/second or hertz. 1/second or hertz. Okay, let's count number of cycles. For example, I'm going to pick this point. Okay, and I'm going to ask myself, how many cycles are passing there, passing that point? Okay, this is going to be 1 cycle. Okay, so if you're standing somewhere here, you see only 1 cycle passing you in 1 second. So it will be 1 cycle per 1 second. Okay, so 1 cycle per 1 second, and that's going to be, the frequency is going to be equal to 1. Okay, now how about the second one? The second one, you have 1 cycle. Next, this is going to be the second cycle. And for example, that one is going to be the third cycle. So I decided to pick that point and count number of cycles that they are passing me. So I'm going to say I have 3 cycles per 1 second. Okay. So let's assume that star representing 1 second far of the starting from the starting point. Okay, so I got three cycles per second. So I'm going to say the frequency in this case is going to be 3. Okay, 3, and then unit, it will be 1/second or 3 hertz. Okay, 3 hertz, and that's going to be the unit of technically the frequency. Okay, what's the relationship between frequency and wavelength? Okay, we say C is going to be equal to wavelength multiply frequency. Okay, remember, lambda represent the wavelength, and the unit for wavelength, it will be in meter. How about the frequency? The frequency, it will be in 1/second. So you say multiply 1/second. What do we get? We get meter over second. And remember, like meter over second is a unit of speed or velocity. So C is going to be velocity technically. And yes, it's a velocity, it's a constant number. Okay, that's a constant number, and it's velocity of light. So C is velocity of light, and this is the number for it. 3 multiplied 10 to the 8th, and it's going to be meter over second. Okay, now what's the relationship between frequency and wavelength? Okay, let's write this. So we have C equal to lambda multiply frequency. Okay, and what's going to be the wavelength? Wavelength, it will be C over frequency. C over frequency. Remember, C is constant. So our numerator is not going to change. Let's highlight the numerator. But the denominator is the one that can go up and down. Okay, now I'm going to say if frequency goes up, what will happen with lambda? Okay, You take C, you divide it by frequency. Frequency went up because C is not changing. It will give you smaller, okay? It will give you smaller wavelength. So as the frequency go up, the wavelength is going to be shorter, okay? Do we have a proof for it? Let's go back, okay? The top one, this was the wavelength when we had the frequency almost 1.25 maybe. Okay, now when I made the waves closest to each other, or I increased the frequency from 1 to 3, as you see, the distance between two maximum points got shrink. And now this is going to be the wavelength. Okay, clearly wavelength for the second one is smaller than the first one. If I call this one 1, I call this one 2. Wavelength for the second wave is smaller. Okay, why smaller? Because we increased the frequency. Okay, so as the frequency goes up, wavelength is going to go down. Again, if, okay, we're going to say if frequency goes down, if you stretch the wave, okay, you stretch the wave, you drop number of frequencies. In that case, wavelength is going to be C over nu. Nu went down. That's going to give you lambda that's got stretched or bigger. Okay, so the wavelength is going to be longer as you decrease, the frequency. That's one fact that we need to know about wave and frequency. Next one is going to be energy. Okay, what's the relationship between energy and frequency? Energy is equal to h nu. And what's the h? It's the Planck constant, and it's 6.626 multiplied 10 to the power of minus 34. And the unit for it is joule to second. So h is a constant number. And how about nu is going to be the frequency? Okay, and unit for nu it will be 1 over second. Okay, let's take the energy. We have joule to second multiply wavelength, which is 1 over second. We're going to cancel second by second, and that's going to give us joule. Okay, and that's the right unit for energy. So this one is energy, and the unit for it will be in joule. Okay, again, what's the relationship between wavelength and this time energy? Okay, so you're going to say energy directly connected to wavelength. Sorry, frequency, my bad, frequency. What does it mean? Okay, it means if frequency goes up, okay, which is equal to dropping the wavelength, okay, that's gonna increase the energy. So as the frequency goes up, okay, we know wavelength is gonna go down, energy will go up. Next, we're gonna say if frequency goes down, which is equal to higher wavelength or longer wavelength, that's gonna give you smaller energy. Okay, smaller energy. So let's summarize what we said until now. First, we said wavelength and frequency are inversely connected to each other. Wavelength and frequency inversely connected to each other. Or you can say frequency wave is equal to 1 over nu. Okay, that's one. And the second thing, we said C equal to lambda multiplied frequency. Next, we said energy is equal to h nu. Energy directly subject to frequency. Okay. Now, I want to know what will happen if I play with the wavelength. Okay, let's call this one 1 and call this one 2 and pair those two. So we're going to get energy equal to h multiplied. Okay, here we want to have actually the nu is going to be equal to c over lambda. Okay, so whenever you see nu replaced by c over lambda, c divided by lambda, and that's going to give us energy equal to hc divided by lambda. Okay, highlight hc. H is a constant number. C also velocity of light. So entire of this piece, entire of the numerator is going to be a constant number. That's going to be constant. It's not going to change. Now, what will happen if I increase the wavelength? So I'm going to say if wavelength goes up, in that case, energy will be divided by a bigger number. So that's going to give you, okay, sorry, HC, my bad. HC will be divided by a bigger number, and that's going to give you smaller energy. So as wavelength goes up, energy will go down. And you can say if wavelength goes down, because energy inversely connected to the wavelength, that's going to give you higher amount of energy. now that we know the relationship between wavelength, frequency, and energy, okay, we're going to go after different techniques that we use in, like in organic chemistry to characterize organic molecules. Okay, it depends on the wavelength that you are using. You can target a specific, spec of any chemical compound. Okay, and for example, if you want to know, let's say about stuff that they're related to the nucleus, you need to use higher amount of energy, and the energy should be something like something around X-ray, for example. Okay, X-ray or gamma. Why? Because you're going to get so close to the nucleus, and the energy, it has to be really high. Okay, and or I want to know, for example, I want to know how the atoms are connected to each other, how carbon, hydrogen are connected to each other. One technique that we use it a lot, we call it NMR techniques. Or you want to know the functional group, then you're going to use that one. Okay, again, it depends to the wavelength. You will get different results, different properties about any molecule, and all of them are like useful. It depends what you want actually to get from that technique. Okay, so as I said, if you want to know whether, for example, nitrogen is attached to two hydrogens, okay, two hydrogen and a carbon, or for example, carbon attached to two hydrogens, and nitrogen is attached to only one hydrogen, the technique that you can use, it will be NMR. Nuclear magnetic resonance is going to tell you how many hydrogens are attached to carbon or nitrogen. If you want to know functional group, you will use IR. If you want to know, okay, for example, whether you have a double bond, two double or three double bonds. Okay, so let's say we have such a system. We have a ring. Okay, and those double bonds, they can move. You can have a resonance. Okay, and you want to actually go after such a structure that it has two or more double bonds. You can use a UV technique, vis technique to identify to characterize technically that compound. Or for example, you have such a compound. You have nitrogen attached to carbon, and that carbon, it has, let's say, hydrogen here. We have CH3 there. Okay, and then nitrogen, it has, let's say, CH3. Okay, of course, we do have a lone pair here. Okay, now I want to know, for example, whether this, molecule, or we call it ligand, okay, ligand, okay, is attached to a piece of metal. Okay, I want to know whether that one attached to the piece of metal, yes or no. Okay, you're going to go after IR technique. Okay, or, also you can go after an UV vis technique, and that's going to tell you whether, the nitrogen is attached to iron or not. Okay, so both IR and NMR can help you. It doesn't mean, both IR and UV vis can help you. It doesn't mean NMR it cannot. Techniques that we are going to use, we call it IR. In IR, we're going to be dealing with vibrational energy. Okay, so energy is coming to the molecule. It will hit the molecule. Now, when it hit the molecule will get some energy and now start to technically vibrate. Okay, and what will happen with a chemical bond? Okay, so imagine my arm. This one is one chemical bond. That chemical bond, it can get shorter. Okay, this bond is it gets shorter, or maybe it gets stretched and it gets longer. So we will have some vibration. Okay, now imagine I have another bond and this one. Okay, so in this case, you give me energy. Okay, I'm gonna say one, while my right hand is coming actually to my side, the left hand is getting far. Okay, so I can actually get such a vibration. Or how about this? Both of them, they are going far. like far from my body at the same time or coming back at the same time. Okay, we call it symmetrical, or it can be that way. Okay, that's another one. Okay, how about this? Well, my right hand is going up and this one is going down. That's possible. Okay, that's possible. And the thing that here is changing is the bond angle. If bond angle is changing, you will have different polarity. Okay, different polarity. Or mu is not going to be equal to 0. And if mu is changing, then that molecule is going to absorb some energy. Okay, and so it can be stretching. It can be like, bending. You're bending bond angle, or sometimes, so you have two bonds. One is coming to your side, and the second one is going back of the plane. Okay, so they can just simply, stretch, or they can, like get closer to each other, or while one is coming to you, the second one is getting back, and the bond angle also, it can change. Okay, so we have all those modes of vibration. Okay, all of them are possible, and each of them is going to ask for a specific amount of energy. In organic chemistry, we can use those actually tiny energy and characterize compounds. Okay, now it depends what attached to like to neighbor, and it depends on the atoms that are attached to each other, or the difference in their electronegativity. We get gap in energy. Okay, that we call here delta E. That gap in energy is going to be specific for example, CH bond versus CO bond, and we can use that gap to say whether we have a carbon hydrogen bond or carbon oxygen bond. Okay, so the gap is going to help us to identify the compound. And the common techniques that we use, we take the compound, the organic compound, we put it on a plate, and that plate, it can be actually kind of like a peel of sodium chloride. So we make kind of like, let's say, a coin by a really hard surface of sodium chloride. We want it to be dry. Okay, and then we put the organic compound on it, and then we use IR instrument to characterize the compound, or you can dissolve it in like in a specific solvent, and that's not gonna technically mess with like our compound. It's just simply dissolving it. That's one way to technically use the IR technique. Okay, I'm going to stop here. In the next lecture, I will be talking about the difference between electronic, vibrational, and rotational techniques, and how we're going to use the IR to go after organic compounds. Thank you very much.